Somewhere in the quiet outskirts of a galaxy, much like our own, a star is ending. It has burned for 10 million years. Not long, by the standards of stars. The sun we orbit will live 1,000 times longer before its own final chapter. But this star was larger, heavier, hungrier. And the cost of that hunger is now being paid all at once, in the span of a single heartbeat. The outer layers bloom outward in a shell of fire. From a great distance, it would look beautiful. A slow, silent flower opening across the dark. But beneath that bloom, in a region no larger than a small moon, something stranger.
For most of its life, the star held itself open by the pressure of its own fire. Every atom in its belly was being squeezed so tightly that hydrogen fused into helium, and helium into carbon, and carbon into oxygen, and on, each stage hotter and faster than the last. The star was a furnace eating itself to stay alive. When at last the furnace reached iron, the bargain ended. Iron will not fuse. Iron only takes. And without new fire, the weight of the star's own body came pressing down, and there was nothing beneath it to hold. In less than 1 second, a region the size of the Earth falls inward to the size of a city. Think of that.
A ball of matter wider than our planet, collapsing in 1 second to a sphere you could drive across in 20 minutes. All of that mass crushed into a space so small that the old rules of matter begin to break. Atoms are not solid things. They are mostly empty room between a tiny nucleus and a cloud of electrons. Under ordinary conditions, that room is inviolable. The electrons keep their distance. They refuse to be pushed too close. But nothing in the old star's core is ordinary anymore. The pressure is so great that electrons are shoved into the protons of each atomic nucleus. They merge. They become neutrons.
The empty spaces in all that matter close like doors being shut all at once, and what remains is a single vast object made almost entirely of neutrons, packed against one another with nothing in between. We call this object a neutron star, and the rest of the old star, the outer layers we spoke of, the shell of fire blooming outward into the dark, does not simply fall away. When the core reaches the hardness of neutron matter, it stops collapsing. It is suddenly, stubbornly rigid. The falling outer layers slam into that wall at a fraction of the speed of light, and they bounce, they explode.
The shock wave tears through the rest of the dying star from the inside out, and for a few weeks, that one point in space will shine brighter than every other star in its home galaxy combined. This is a supernova, a funeral attended by an entire sky. When the light finally fades, months later, years later, what is left behind is a small, dark, almost forgotten thing, the neutron star. A ball of pure collapsed matter, roughly the width of a single city, perhaps 20 kilometers across, perhaps 30. You could hold its dimensions inside the borders of your hometown, and yet it contains, compressed into that city-sized body, more mass than our entire sun. there is something in us that resists a fact like this.
We reach for it, and our hands seem to pass through. The scales do not feel real. We live on a comfortable planet where a mountain is a mountain and an ocean is an ocean, and a handful of dust weighs what a handful of dust should weigh. We have no calibration for what comes next, but the universe does not owe us calibration. It only asks us to keep looking. Out there in the dark, born from the collapse of a giant, a new kind of thing has been left behind. It is cooling now, glowing faintly in X-rays. It is spinning, sometimes hundreds of times each second.
And most of them, most of these small, dense corpses, will live quietly for the rest of cosmic time, slowly fading, becoming more and more invisible. Most of them, but a few of them, perhaps 1 in every 10, perhaps 1 in every 20, are born with something extra, something terrible. A magnetic field so strong that it bends the very vacuum around them into a shape no human has ever touched. These are
The path from that ancient collapse to the storm we will describe is worth dwelling on for a moment longer, because the details of a neutron star's birth are often hurried past, and yet they are the foundation on which every stranger thing will be built. When the core of the dying star began to fall, the fall was not slow and orderly. It was a race. In the innermost kilometer of the collapsing region, the matter was moving inward at a quarter of the speed of light. Photons, which normally dart through matter at the fastest speed anything is allowed, struggled to outrun the infall.
Neutrinos, those ghostly particles born of nuclear reactions, were created in such vast numbers that the collapsing star, for a few brief seconds, was the brightest neutrino source in the entire galaxy. More energy left that dying core in neutrinos than our sun will emit in all forms of radiation over its entire 10 billion year life. Most of that neutrino energy escaped. It passed through the outer layers of the dying star as if those layers were barely there. It passed through any nearby planets. It passed through any nearby witnesses. If you were somehow standing on a hypothetical world at a safe distance from such an explosion, the neutrinos would pass through your body by the trillion, and yet you would feel nothing at all.
They would not warm you. They would not push you. They would simply go through, the way light goes through a clean window, and continue on their way into the wider universe, carrying the final confession of the star that made them. Only a small fraction of that neutrino energy, perhaps a single %, was captured by the outer layers of the star and used to drive the supernova. But a single % at these scales is enough to blow the outer layers apart, to send them expanding outward at thousands of kilometers per second, to paint the nearby sky for years with glowing filaments of hydrogen and oxygen and iron. The corpse at the center, meanwhile, has stopped falling.
The pressure of neutron degeneracy, that stubborn refusal of neutrons to overlap too closely, is all that stands between it and a further collapse into a black hole. Sometimes, if the original star was massive enough, even neutron pressure is not enough, and the collapse continues. A black hole is born. No neutron star remains. But if the mass balance is right, the collapse halts at the neutron stage. The object is stable. It will not collapse further. It will sit for the rest of cosmic time as a small, rigid corpse the size of a city. That corpse, in the rarest cases, is the seed of a magnetar. Before we can understand the storm a magnetar carries, we must first understand the body that carries it. We must sit with the strangeness of a neutron star, not for a moment, for long enough that the strangeness begins to settle in. Imagine that you could, somehow, reach down to the surface of one of these objects. Imagine a hand as strong as starlight, gloved against all the violence of it, lowering a single small spoon to the place where the crust meets the sky of vacuum. Imagine scooping up a single spoonful of that crust. A little, shining, silvery sample, no larger than the portion you might take with your breakfast. Now lift it. Bring it back to the soft ground of our world.
That spoonful would weigh, by the most careful estimates, about 1 billion tons. 1 billion tons. Placed inside a spoon. There is no language for that in the vocabulary our ancestors built for us. Our words for weight were trained on stones, on carts, on grain sacks, on the modest burden a single animal could pull. Even the word ton sounds, at its root, like something you could picture if you tried. A small car, a large bull, a heavy piece of furniture. A ton is just barely inside the range of the imagination. A billion tons is not inside any range. Perhaps this will help. Take the highest mountain on our world. Take Everest. All of it, from its deep roots to the thin, dry air at its peak.
Every ice field, every cliff, every stone the size of a house, every grain of ice and dust, every hidden body of a climber who never came back, all of it. Now compress that mountain. Not crush it. Do not picture violence.
A neutron star takes that word and pushes it past the edge of thought. It is full in a way that makes ordinary full look empty. To make this matter, the old laws of the atom had to be overruled. You and I are made of atoms. A human body contains something on the order of 7 times 10 to the 27 atoms. 7 octillion. That is a number large enough to swallow. But each of those atoms is, in its bones, almost nothing. If you took a single atom in your hand and blew it up to the size of a cathedral, the nucleus at its center would be no larger than a grain of rice hovering in the middle of the dome.
The rest, the cathedral, is empty air. You are mostly empty space. I am mostly empty space. The chair you sit in, the floor beneath it, the bread you ate this morning, everything solid that has ever touched you is, at the deepest level, 99.9999% nothing.
The only reason the floor does not let you through is that the electrons in the atoms of the floor refuse to overlap with the electrons in the atoms of your shoe. They resist. They shove. That refusal is the hard thing we have called matter. Inside a neutron star, that refusal is broken. The pressure is so enormous that the electrons are forced to merge with the protons. The empty cathedrals collapse.
The grains of rice at their centers are packed directly against each other, until all that remains is one continuous sea of neutrons touching neutrons, a single structure of almost unimaginable hardness, with the last traces of emptiness squeezed out of it. You are looking at a state of matter that existed nowhere in the first 3 minutes of time. You are looking at something that our everyday universe usually refuses to build. The scale of a neutron star is just as unsettling as its weight. Roughly 20 kilometers across, a sphere you could drive a car around in half an hour if its surface were calm. Yet inside that small ball, there is more mass than the sun that warms our faces. Our sun is wider than 100 Earths stacked end to end. Pour all of that solar fire into a city block, and you begin to approach the substance in question. Now imagine standing for a foolish moment on such a body. You would not stand for long. You would not stand at all. The gravity at the surface of a neutron star is so ferocious that a person, dropped from even a small height, would not strike the crust so much as be unmade by it. Before the body could reach the ground, it would be stretched and accelerated to a speed near a significant fraction of that of light, and on arrival would release a burst of energy equal to a large nuclear weapon.
The atoms of the visitor would not bounce. They would simply be added to the star's surface, a quiet, small new layer, no thicker than a film of paint. That is the body. That is the vessel. Before we speak of fields, before we speak of storms, before we speak of what it means for such a thing to also carry a magnetic soul, we must simply let the body exist in our minds as what it is. A city-sized object that weighs more than the sun. A crust so dense that a spoonful holds a mountain. A surface where a human being would exist only for the amount of time it takes to be erased. And all of this is only the beginning.
All of this is what the universe sometimes makes, even when it is not trying very hard. Most neutron stars, the great quiet majority of them, live out long lives with nothing more than this. They are already in their ordinary form, the most extreme dead things our cosmos has on general offer. But some of them, as we are about to learn, are not content with being extreme. Some of them are a kind of weapon.
Before we move on, one more small meditation on density is in order, because the number we are about to carry with us through the rest of this journey is so large, so unlike anything in human experience, that it deserves to be turned in the hand one more time, examined from another angle, before it is let go of. The neutron star we have been describing is so dense that if you could somehow take the entire human population, all 8 billion of us, and remove the empty space from our atoms, the space between nucleus and electron, the vast cathedrals of nothing that make up most of our apparent solidity, the resulting compressed lump would fit inside a sugar cube.
8 billion lives
in all their height and weight and breadth, reduced to the volume of a single crystal of sucrose. That is how much of us is truly there, and how much is empty room. A neutron star is what matter looks like when that empty room has been taken away. And yet, strangely, a neutron star is not the densest thing the universe can make. A black hole is denser. Or rather, a black hole is what happens when there is no density left, because all the matter has fallen into a single point beyond which even our mathematics begins to tremble. A neutron star is the last stable state before that tremble. It is matter at the end of its endurance. One more step toward compression, and it would cease to be matter at all. A neutron star is balanced on the edge of the cliff. It has not gone over, but it is leaning. And what holds it from going over is, in part, the same quantum rule that keeps your shoes from passing through the floor. The Pauli exclusion principle, that deep property of neutrons as of electrons that refuses to let two of them occupy the same quantum state. At the density of a neutron star, this refusal is straining against gravity. Every cubic centimeter of the interior is a small, slow war, neutron degeneracy versus the crushing weight of the object itself. And it is, for most such stars, a stalemate. The war does not end.
The war does not resolve. The star, as long as it exists, is a frozen moment of conflict. A single photograph of two forces pressing against one another, and neither giving way. Inside that frozen photograph, in the rarest cases, a magnetic storm was locked in at the moment of birth, and the storm, unlike the force balance, does not last forever. The storm is the part of the magnetar that will, over time, die.
Before we approach the magnetar directly, it is useful to see it in its proper family. Neutron stars are not all alike. The same collapse, the same violent birth, produces different children depending on small differences in how the star was spinning, how it was tangled, how its outer layers fell. There are, in a broad sense, three faces of the neutron star. Three ways the universe can wear this corpse. The first face is the ordinary neutron star. This is the quiet one. It sits in space, perhaps at the center of a faintly glowing cloud of debris left behind by the supernova. It is slowly cooling.
It is spinning at some modest rate, perhaps turning on its axis a few times every second, or only once every few seconds. It has a magnetic field, yes, but the field is modest, at least by the standards we are about to see. It is no larger than the fields produced in the strongest laboratories human beings have ever built. These objects are so quiet, in fact, that many of them are nearly impossible to find. We know they are out there by the millions in our galaxy. We have only ever directly noticed a few thousand. The rest drift in the dark, undetected, content to be the unremarked bones of stars.
A pulsar is a neutron star that has chosen to blink at us. When a neutron star forms, the laws of physics demand that it spin. The original star was large. It had angular momentum, the quantity of turning stored in its mass. When the core collapsed, that turning did not disappear. It tightened. An ice skater pulling in her arms, spinning faster.
The star has pulled in its arms by many thousands of times, and so it spins many thousands of times faster than it did before. Some pulsars turn hundreds of times per second. Some, the very fastest so-called millisecond pulsars, turn more than 700 times every second. If you could stand nearby, unharmed, you would feel no rotation.
It would be too fast for any eye to catch. Only by listening to its signal could you know you were watching something move. Now place a magnetic field on this rapidly spinning object. The field has poles, much like the field of our own planet. From each pole, a beam of radio waves and high-energy particles streams out into space. As the star turns, those beams sweep the sky like the light from a lighthouse. If purely by chance, one of those beams happens to be aimed in the direction of Earth, we see a pulse, a brief flash, another pulse, another flash, perfectly regular.
So regular that the first astronomers who caught one in 1967 briefly wondered if they had heard a message from another civilization. They called it, half seriously, LGM-1, Little Green Men 1. It was not little green men. It was something in its own way, stranger. It was a dead star, spinning itself into a clock of such precision that it rivals the best atomic timepieces on Earth. Some pulsars have been measured keeping time for decades, and their beats are reliable to an accuracy finer than 1 part in a trillion. A star slowly becoming a metronome. The universe keeping rhythm with the corpses of its own children. The third face is the Magnetar. This is the rarest face.
This is the one we have come to meet. A magnetar is a neutron star whose magnetic field has, for reasons still not fully understood, been pushed to values that would be laughable in any human laboratory. Ordinary pulsars carry fields of roughly 10 to the 8th Tesla. A strong medical scanner, by comparison, operates at a few Tesla. A household magnet, the kind clinging to a refrigerator door, is a small fraction of 1 Tesla. A pulsar's field, then, is already 100 million times stronger than anything a hospital can make. A magnetar's field can be 1,000 times stronger still. We will look at this number more carefully soon. For now, let us simply hold it in the mind. A pulsar is a star with a clock.
A magnetar is a star with a storm, and the storm is of a kind that bends the space around it into a shape where the ordinary laws of matter can barely survive. All 3 faces come from the same death. All 3 are made of the same dense neutron stuff. But the small differences in how they are born, the final alignment of spin and field and crust, write 3 entirely different endings for the same story. Magnetars are born from the same collapse, but they are the rare cousins. Most neutron stars are quiet. Some are clocks. A handful are unlit furnaces of electromagnetic power. Knowing the difference is like knowing the difference between 3 old men sitting on the same bench. One reads the paper in silence.
One taps his cane on the ground, keeping time for a song no one else hears. One, very rarely, opens his coat and reveals that he is made entirely of fire. Each of these 3 faces tells us something different about how the universe handles its endings. The ordinary neutron star teaches us that even in death, most things simply go quiet. They do not perform. They do not announce themselves. They simply exist, dimming over long time scales, keeping their secrets as the galaxy wheels around them. The pulsar teaches us that even in death, some things find a rhythm, become clocks, lend themselves to the slow measurement of time. The Magnetar teaches us the third lesson, the least comfortable one, that even in death, some things are still violent.
That the grave, in rare cases, is not silent but loud, not cold but fierce, not at rest but full of an unspent storm. We should also say, because it will matter later, that these categories are not fixed. A magnetar ages into something that looks, eventually, like an ordinary neutron star. A pulsar, given enough time, slows down and stops emitting its beams. Neutron stars change their faces over millions and billions of years. The categories are snapshots. They describe what an object looks like at a particular moment in its life. Some astronomers have even proposed that certain very slow pulsars might be old magnetars, their fields now weakened to the point where they behave like ordinary neutron stars with unusually strong fields.
If this is right, then any given quiet neutron star we see today might have been a magnetar once, tens of thousands of years ago, back when the fury was still fresh. The quiet old man on the bench might have been the man of fire long ago, before the coals cooled. This is a gentle reminder that we should be careful with the stories we tell about any cosmic body. The universe does not honor the categories we build. It flows between them, slowly. Every object we name is a freeze frame, a still photograph pulled from a much longer film. The film keeps moving, whether we are watching or not. In the case of magnetars, the film is especially strange.
Because the loudness that makes them magnetars is temporary, because the field decays, because their violent character is a passing phase, they are not simply objects. They are episodes. They are stories the universe tells, for about 10,000 years, in very particular places. Before that, they were just collapsing cores. After that, they are just neutron stars. During that narrow window, they are the most intense magnetic phenomenon the cosmos is known to produce. We are, in other words, lucky to live at a time when any magnetars exist at all. In the far future, when all the current ones have decayed and no new massive stars are being born to replace them, there will simply be no magnetars left in the universe. They will all have become quiet.
The third face will close its eyes for the last time, and the gallery of cosmic faces will be reduced to two.
If the magnetar is rare, how rare is it? Exactly. Our galaxy, the Milky Way, contains somewhere between 100 billion and 400 billion stars. Most are smaller than our sun, red dwarfs, burning slowly at the bottom of the scale. A minority are larger. An even smaller minority are large enough to end their lives in the collapse we have described. Over the long history of our galaxy, this has produced an enormous population of neutron stars. Most estimates place the number somewhere around 1 billion. A billion small collapsed corpses, scattered through the disk, most too dim and too cold to see. Out of that billion, we have directly observed only a few thousand as pulsars, because only those whose beams sweep our planet can be detected.
The rest remain invisible to us, though we know they are out there, more or less distributed, like everything else in the galactic disk.
Out of that same billion, the number we have identified as magnetars is, at the time of this recording, about 30. 30 known magnetars. In a galaxy of 1 billion neutron stars. In a galaxy of hundreds of billions of ordinary stars. The rarity is almost absurd. If you picked up every star in our galaxy and placed it in a very large bag and reached in blindly, your chances of pulling out a magnetar would be less than 1 in 10 billion.
By some estimates, there may be a few thousand more magnetars hiding in the galaxy that we have simply not noticed yet, because magnetars, unlike pulsars, are often not steady beacons. They flare. They go silent. They lurk. They reveal themselves only when their storms happen to break against our instruments at a time we are watching. Some might spend centuries in quiet, then release a single burst, then go quiet again, slipping back into darkness. So the true count might be higher, but the essential fact does not change. Of all the stars in our galaxy, an almost vanishing fraction end their lives with the kind of magnetic violence we are about to describe.
If the heavens offered us an infinity of graveyards, only a scattering of them would hold a magnetar. Most collapsed stars live in silence. Magnetars are the exception that does not want to be ignored. Rarity, in a universe this old and this large, is a kind of strangeness all its own. Most things we see once, we tend to see again. Spiral galaxies, yellow stars, rocky planets, ice in shadowed craters. Nature repeats its favorites. But when nature makes a magnetar, it seems to be making something it only makes reluctantly, something that is not a staple of the cosmic diet. Perhaps the conditions that produce them are unusually rare. Perhaps the star must be spinning at just the right speed, at just the right moment of collapse.
Perhaps the magnetic seeds must be arranged in just the right tangles. We will return to this puzzle later. For now, it is enough to say that somewhere in our own neighborhood, there are objects so uncommon that even a galaxy as full as ours has made only a handful of them. And they are, quite likely, the deadliest thing it has ever built.
We have come a long way without actually measuring the magnetic field of a magnetar. It is time. To understand the number, we need a simple unit, the Tesla. 1 Tesla is a measure of magnetic strength, named for Nikola Tesla, a man who himself once tried to pluck lightning out of the sky. Do not worry about the formal definition. It is enough to know that 1 Tesla is a very strong field, by the standards of everyday life. A Tesla is more than 10,000 times the strength of the magnetic field of our own planet. Our planet, the Earth we walk on, has a magnetic field. It is what aligns compass needles. It is what directs the wandering of migratory birds.
It is what shields us high above from the charged particles of the solar wind. Its strength at the surface is roughly 50 microtesla, 50 millionths of a Tesla. Small, but everywhere. A soft planetary blanket of invisible direction woven by currents in our iron core. If you lift a refrigerator magnet off its door, you are handling a field of about 1/100th of a Tesla, several hundred times stronger than the field of the whole planet beneath you, but small compared to the strongest machines we have built. A medical imaging scanner, the large ring patients climb into for a clearer picture of a knee or a brain, operates at perhaps 1.5 Tesla.
Some advanced scanners push past 3 Tesla, and experimental research magnets have reached sustained fields of around 45 Tesla, generating a low, steady hum of power and refrigerating their superconducting coils with liquid helium. This is roughly the limit of what human beings can build and hold steady. For a brief moment, in pulsed magnets designed for a single shot of power, laboratories have pushed the field to 1,000, perhaps a little over Tesla, before the apparatus breaks under the force of its own field. That is the human edge of the possibility. About 1,000 Tesla, for an instant, in a machine that destroys itself in the effort. Now consider the magnetar.
The magnetic field at the surface of a typical magnetar is approximately 10 to the 11th Tesla. 100 billion Tesla. Let that number lean against the others for a moment. A refrigerator magnet, 1/100th of a Tesla. A hospital scanner, 3. A laboratory record, 1,000, briefly. A neutron star that happens to be a pulsar, perhaps 100 million Tesla, 100,000 times stronger than anything we have ever built. And the magnetar. 100 billion Tesla. Let us try to build intuition with a different comparison. The magnetic field of our planet is about 50 microtesla. The magnetic field at the surface of a magnetar is about 2,000 billion times stronger than the field you live inside. Not 2,000 times.
Not 2 million times. 2,000 billion times. A number with 21 zeros between the 1 and the decimal point if you write it out. You cannot visualize this. No one can. The human brain, trained on the fields we bathe in every day, was never built to model a factor of 10 to the 21. The most we can do is understand, in a general way, that we are being asked to compare a whisper to every sound that has ever been made, including the sounds that will be made tomorrow, and that even this comparison is inadequate. And yet, this is only the field at the surface.
Inside the star, beneath the crust, in regions we can only guess at, the field is likely stronger still. In some magnetars, models suggest internal field strengths that approach the theoretical limit set by the strength of the nuclear interactions themselves. At that point, the universe starts to behave in ways that are not in any ordinary physics textbook. Atoms change shape. Space itself develops new properties. Light passing through begins to split into polarizations that behave, quite literally, like different substances. We will come to all of that. For now, let the number simply sit. 100 billion Tesla.
A storm larger than the sum of every storm humans have ever measured. Every storm our world has ever made. Every storm all our best machines have ever been able to approximate. A storm that a teaspoon of matter cannot hold, that a planet cannot hold, that most stars cannot hold. A storm that has somehow been locked inside a dead object the size of a city and allowed to sit there, turning for 10,000 years at a time. There is an old, odd emotion that rises in a person when they meet a number like this. Not only awe, but something more personal. The quiet, uneasy sense that one was not invited. That this is not a place for us.
That we have wandered briefly into a room meant for someone else, and everything in the room is very old and very quiet and very powerful, and it does not know or care that we are here. Magnetars do not know we exist. Magnetars are not aware of us at all. But the fields they carry have the power, if the distance were small enough,
to end us in ways that no human weapon could match. Another way to approach the scale of the magnetar's field is through energy. A magnetic field carries energy. You can feel this, in a small way, by holding two strong magnets close together and letting them snap shut.
The click you feel is the field giving up some of its stored energy as motion and sound. In a magnetar, the energy stored in the field is, by any terrestrial standard, simply enormous. The total magnetic energy stored in a single magnetar is approximately 10 to the 47 joules. To give this a point of comparison, the total electrical energy generated by all of human civilization, from the first small electric lights of the late 1800s to the present day, is a number that would fit comfortably inside a single second of a magnetar's magnetic energy release, if the magnetar chose to release it.
Our entire industrial civilization, with all its cities and factories and server farms, with every lamp and every refrigerator and every engine, is a modest little bead of activity compared to the steady reservoir of energy in a magnetar's field. If you could somehow extract the magnetic energy from a single magnetar and use it to power a planet at a civilization level, you could power that planet for a length of time that exceeds the current age of the universe. A magnetar's field, in other words, is an energy reservoir on a scale that makes every human ambition look small and makes every stellar engine look limited. And this reservoir is, most of the time, simply sitting there.
The magnetar is not actively radiating all of its field energy at once. Most of the field remains bottled up inside the star, threaded through the crust and the neutron interior, pinned in place by the rigid structure of the body. Only when the crust cracks, only during a starquake, is a portion of that reservoir released. When you read, then, that a giant flare from a magnetar can release more energy in 1/10 of a second than the sun releases in 200,000 years, you are reading a statement about a single small crack in the crust of the object, a single small adjustment of the field, a minor rearrangement. And the universe, for a brief instant, brightens a region around it larger than any ordinary galaxy.
One can only look at numbers like these and feel something between reverence and vertigo. The scale of what a magnetar contains is, by ordinary standards, almost theological in its weight. A single dead object, smaller than a city, carrying more energy than our civilization will ever produce, ready to spill a small fraction of it whenever its crust takes too much strain. This is not a machine. This is not a tool. This is simply what the universe, in its rare moods, occasionally makes.
Imagine that we could somehow travel toward a magnetar, that we had a ship impossibly strong, shielded in ways no metal can be shielded, with instruments capable of reading out what happens to ordinary matter as we approached. What would we see? For a long time, nothing unusual. Magnetars are dim. Most emit most of their energy in X-rays, which our eyes cannot see. From a distance, the magnetar is simply a point source, like any other star, except slightly redder and slightly fainter than it should be for its spectrum. There is no visible lightning, no aurora, no halo, just a small, sullen speck in the dark. As we draw closer, the instruments begin to whisper. 10,000 kilometers from the surface, the magnetic field
is still ferocious. By any human standard, it would be lethal to technology. Electronic equipment would fail. Electrical currents would run in strange directions. Metals would warm themselves from induced eddy currents as the ship moved. We would feel the field pulling weakly on any loose iron screw. Every compass on board would spin, then melt. We continue, foolishly. 1,000 kilometers from the surface, something more fundamental begins to happen. The atoms in the ship and in our bodies begin to change shape. An atom, recall, is a nucleus surrounded by a cloud of electrons. In ordinary conditions, that cloud is roughly spherical. The electrons move in paths shaped by the pull of the nucleus and the mutual repulsion of one another.
They form a little three-dimensional balloon of probability around the dense center. In human affairs, all of our chemistry, all of our biology, all of our engineering depends on the fact that atoms are roughly little balls. In a magnetic field of modest strength, this remains true. The field nudges the atoms, but does not reshape them. As the field grows stronger, however, the shape of the atom begins to bend. The electrons are charged. A moving charge in a magnetic field is pushed. In a very strong field, that push becomes larger than the force that binds electrons to their nucleus. The electrons cannot roam freely. They are forced into tight spirals. They are driven to follow the lines of the field.
And when this happens, the balloon of the atom deflates in one direction and stretches in another. Atoms in a magnetar's field are not spheres, they are needles. Imagine a strand of iron atoms, here on Earth. On our table, the iron atoms sit side by side in their crystalline lattice, each one a small ball, linked to its neighbors. A gram of iron is a patchwork of these neat, almost uniform bubbles. Now place that gram of iron near the surface of a magnetar. Each atom, instead of remaining a ball, has been squeezed. The electrons are slammed into narrow spirals along the magnetic field lines. The atom is no longer a sphere, but a long, thin stick.
An iron atom in a magnetar field is stretched into a shape longer than it is wide, sometimes by a factor of 100. If you could hold that iron in your hand, it would no longer behave like any iron you have ever known. Its chemistry would be different. Its crystals would no longer form neat cubic lattices. They would form long oriented chains, like hair combed by a giant. Its melting point, its conductivity, its very identity as iron would be half erased. This is not a trick of perception. This is the atom itself, forced by electromagnetic law to abandon its familiar body. Every atom in the ship, every atom in our bodies would be pulled out of shape.
The molecules of water in our blood, the protein chains in our cells, the double helix of our DNA, none of them were built to exist as needles. Their chemistry works because they are spheres and clouds and folds. In the presence of such a field, they would stop working. The bonds that make a protein, the forces that hold the rungs of a genetic ladder in place, would be overrun. Biology would cease, not all at once, but in a soft universal unraveling. There would be no pain. There would be no moment of injury. There would simply and quietly no longer be anything alive to feel it.
This distance of about 1,000 kilometers from the surface of a magnetar is sometimes called the region where atoms themselves are redesigned. Beyond it, toward the star, matter as we know it does not function. The periodic table, that careful human map of all the elements, loses half its meaning. Water is no longer water. Iron is no longer iron. The ship and its crew, if still intact mechanically, would no longer be chemistry at all, but a new kind of stick-thin exotic matter, resembling nothing in our experience. This deformation of atoms has been called, in the technical literature, the formation of an exotic phase of matter. Condensed matter theorists have even given it a name.
Such stretched atomic strands, if they could be arrayed in regular patterns, would form what is sometimes described as magnetic polymers. Chains of atoms strung along the field like pearls on a wire. In some regions of the magnetar's atmosphere, if we could call it an atmosphere, such chains are believed to be the dominant form of matter. The surface layers of a magnetar are not a mist of free gas. They are a crystallized forest of atomic strings, held in place by the field, extending outward along the magnetic lines like iron filings around a laboratory magnet, frozen in that orientation because the field is too strong for them to turn away.
An imaginary hand running along the surface of a magnetar would feel not a smooth iron crust, but a bristling forest of microscopic needles, all pointing the same way, refusing to bend. If that hand tried to brush them sideways, the hand would be destroyed, of course, long before anything as delicate as a sensation of texture could register. But, in the abstract, as a picture, the texture of a magnetar's surface is that of a surface combed by a force infinitely stronger than any comb any craftsman ever built. And around this combed surface, the magnetic field extends outward, shaping the space through which any visitor must pass. We speak loosely of a magnetic field being in the object.
In truth, the field permeates everything around the object as well. The field lines reach out into the vacuum, curving and connecting and closing back on themselves, creating a vast magnetosphere around the magnetar that is itself, effectively, a region where the laws of the universe have been modified. Astronomers sometimes draw diagrams of magnetospheres with their twisted rope-like structures, their closed field loops, their open field lines streaming away into space. These diagrams are useful, but they fail to convey the scale. In reality, the magnetosphere of a magnetar extends for hundreds of kilometers around the body itself, and inside that region, the vacuum is not really a vacuum at all.
It is a strained, polarized, alive in a sense, with virtual particles reacting to the field, forming and dissolving, altering the speed of light by small but measurable amounts. This is, in some sense, the territory of the magnetar. The body itself is small. But the region of space the magnetar controls, in which its fields dominate the behavior of matter and light, is a region thousands of times larger than the object itself. A magnetar, in the full accounting of its presence, is not a city-sized object. It is a city-sized object surrounded by a planet-sized envelope of altered physics. To approach a magnetar is not to approach a point. It is to approach a world, invisible to ordinary eyes, in which the familiar rules have been rewritten by the mere fact of the field, and still the magnetar does not notice. It turns on its axis, perhaps once every 5 seconds, perhaps once every 10. It goes about the long, slow business of cooling and dimming, unaware that anything was approaching.
Its field is not a trap set by a malevolent builder. It is simply the honest structure of the object. A ship pressed against it is like a moth pressed against a blowtorch. The flame is not aimed at the moth, but the moth is gone all the same.
On the 27th of December, in the year 2004, an instrument aboard a spacecraft orbiting the Earth recorded a flash of gamma rays unlike any that had ever been observed. It came from the constellation Sagittarius, from a magnetar known as SGR 1806-20. The star was almost 50,000 light-years away. Very far by human standards. Very far from any place we have ever touched. And yet the flash, lasting only a tenth of a second, lit up the upper atmosphere of the Earth so thoroughly that satellites orbiting above our planet were briefly blinded. The ionosphere rang. Radio signals were disrupted.
The sky, in an instant, had been struck by something that no star had struck it with in remembered history. In that tenth of a second, SGR 1806-20 released more energy than our sun will release in the next 200,000 years. More, in fact, than all the stars of the Milky Way combined release in a tenth of a second. All of this from a single flick of a dead star 50,000 light-years away. All of this while most of us were asleep, or walking, or pouring coffee, or doing the small, ordinary things a late December morning holds. What had happened? What could cause an object to release, in a heartbeat, more light than every other star in its galaxy?
The answer is called a starquake. A magnetar's crust is, as we have said, unimaginably dense. The weight of a mountain in a spoon. But it is also rigid, brittle, crystalline. It is, in a sense, a single solid shell of iron, compressed to insane hardness, floating on the sea of neutron matter within. The field that threads this crust is anchored to the material. The field and the solid crust are bound together. As the star rotates, as centuries pass, the interior of the magnetar continues to rearrange itself. The magnetic field shifts and buckles. It tightens in some places and loosens in others. Strain builds up in the crust. It can only take so much. At some point, in a single terrifying second, the crust cracks.
An earthquake, on our world, is the slipping of two continental plates, releasing energy stored over years of slow pressure. A starquake, on a magnetar, is the snapping of a crust 10 billion times denser than stone, under the pressure of a field 100 billion times stronger than anything the Earth can make. When the crust snaps, the magnetic field lines attached to it snap too. They reconnect. They release their stored energy. They shoot out waves of electromagnetic power that in the case of SGR 1806-20 struck the Earth from half a galaxy away. This is what a starquake looks like from a distance. A flash in gamma rays. A disturbance in the upper air of our planet.
The numbers that we must multiply together to understand it are so large that writing them out feels childish. But now imagine watching that same event from much closer. Imagine standing safely at a distance of, say,
1 light year from the magnetar when it quakes. A single light year. Close enough that the light will reach you in a year, but far enough that, in any reasonable sense, you are not even in the same cosmic neighborhood. At that distance, the flash is still strong enough to sterilize an unshielded planet, to strip it of its ozone, to ionize its atmosphere, to flood its surface with a sheet of radiation no living thing could survive.
At a distance of 100 light years, the effects are reduced, but still deeply dangerous. Models suggest that a flash like the one from SGR 1806-20 at 100 light years would be a biosphere-altering event. Not a tenth of a second of discomfort, but a sudden puncture in the shield of life. At 10 light years, the models blur into honesty. No known biology would survive unscreened. This is how we now measure the power of a magnetar. Not in brightness, not in warmth, but in terms of how far away a planet would have to be before one of its quakes could pass through the sky without burning everything under it. The great comfort of our situation is that no magnetar lives nearby. The closest magnetar we know of is thousands of light years away, far enough that even the worst bursts we have observed reach us as brief taps, noticed only by instruments built to catch them. Our upper atmosphere has wobbled once or twice from their touch. Nothing worse than that. We exist because no magnetar was placed in our backyard. It is worth pausing on the mechanics of the starquake itself, because the picture is stranger than we might at first realize. On Earth, when an earthquake occurs, the ground shakes because 2 plates of rock have slipped past each other, releasing stored elastic energy as seismic waves.
Those waves travel through the crust at speeds of a few kilometers per second. They ring buildings. They topple walls, but their energy is rapidly absorbed by the continents themselves, and within hours or days, the ground is quiet again. A starquake is a different beast entirely. The crust of a magnetar is 10 billion times denser than rock, and perhaps 10 times stronger in terms of its tensile limit. When it cracks, the energy released is not measured in kilotons or megatons, but in units many orders of magnitude larger. And the energy does not simply rattle a structure. It reconfigures the magnetic field itself in an instant over a region surrounding the star.
Models of these events suggest that the cracking of the crust happens in less than a millisecond, 1,000th of a second. During that brief interval, a crack perhaps a kilometer long opens across the surface, and the magnetic field lines anchored to that region are suddenly free to rearrange. They snap. They reconnect. They release an enormous pulse of electromagnetic energy outward into the magnetosphere. That pulse, in turn, accelerates charged particles to near the speed of light. Those particles, spiraling along the newly reconnected field lines, emit gamma rays. The gamma rays pour outward into space in a cone, carrying the signature of the event to distant observers. From the outside, all we see is a flash, 1/10 of a second of gamma rays.
But inside the star, that flash was the culmination of years or centuries of slow magnetic strain, released in a single catastrophic adjustment of the crust. Some magnetar quakes are small. These are called bursts, and they happen fairly often, sometimes several times a day in an active magnetar. They are detected by orbiting X-ray observatories as brief spikes in the record. They disturb nothing in our atmosphere. They are almost routine, from the magnetar's point of view, the equivalent of a small tremor, a minor readjustment. Other quakes are larger. These are sometimes called intermediate flares, and they occur perhaps once a year in an active source. They release significantly more energy than the small bursts, but still not enough to pose any threat to distant planets.
A tiny handful of quakes, perhaps only 3 or 4 observed in the entire history of modern astronomy, are called giant flares. These are the events that release more energy in a fraction of a second than our sun does in hundreds of thousands of years. They are the ones that have reached us from across the galaxy, knocking briefly against our atmosphere, ringing in our instruments, reminding us that some stars in their rare moments can speak loudly enough to be heard from a great distance. It is worth letting that fact settle. Life on Earth, in all of its unremarkable green abundance, persists partly because, out of a galaxy full of wonders and hazards, none of the 30 known magnetars happen to be close enough to trouble us.
It is a kind of luck most beings would not understand they had, because we have never been without it. It is, in its way, a silent gift from the geometry of space. The magnetars are far. Keep breathing, the universe says. I have placed the fires elsewhere. It is worth pausing. Also, on the question of how we came to know about magnetars at all, because these objects do not broadcast themselves the way our sun does. They do not fill the sky with light. They are found only through careful instrument work, over decades, by thousands of astronomers painstakingly assembling small pieces of evidence.
The first hints of their existence came in the late 1970s and early 1980s, when satellite detectors observed strange bursts of gamma rays coming from directions in the sky where no known sources lived. These were called soft gamma repeaters, because unlike the more famous gamma ray bursts, which appear once and never again from the same location, these sources repeated. They flashed, they quieted, they flashed again. They seemed to be tied to specific locations. They seemed to be small. At the same time, another class of unusual X-ray sources was being catalogued.
These were called anomalous X-ray pulsars, because they were clearly neutron stars, clearly pulsing, and yet they radiated far more energy than their slow rotations could possibly supply through the normal mechanisms of a pulsar. Their spin-down rates were not fast enough to power their glow. Something else had to be the source of their energy. In 1992, 2 astrophysicists, Robert Duncan and Christopher Thomson, proposed a unifying theory. Both the soft gamma repeaters and the anomalous X-ray pulsars, they argued, were the same kind of object. Young neutron stars with enormous magnetic fields. Magnetars. The fields themselves were the energy source. The decay of those fields and the starquakes they produced explained both the bursts and the steady X-ray glow.
It took another decade or more for the theory to be broadly confirmed. By the early 2000s, measurements of the spin-down rates and the burst energies of several sources had solidified the picture. Magnetars were real. The universe did, in fact, produce objects with fields 1,000 times stronger than ordinary pulsars, and these objects were responsible for some of the most extreme phenomena ever recorded. This is a small reminder that the universe is not a thing we simply see. It is a thing we figure out. Our knowledge of magnetars required telescopes in orbit, statistical analyses of subtle timing variations, theoretical models of nuclear matter under impossible conditions, and the patient work of generations of researchers.
30 objects out of 1 billion neutron stars in a galaxy of hundreds of billions of stars, identified by humans on a small warm planet through instruments of our own making. It is, in its own modest way, a small miracle of curiosity.
By now, a natural question begins to form as we sit with all this strangeness. Where does the field come from? A star collapses. A neutron star forms. Most neutron stars, as we have seen, carry modest fields. Some, the pulsars, carry strong fields. A rare few, the magnetars, carry fields that beggar belief. What is different about the birth of a magnetar? Why does one corpse hold a whisper while another holds a shout? The honest answer is that we do not know. There are, however, two main ideas, and they are beautiful in their own ways. The first is called the dynamo hypothesis. On our own planet, the
Deep below our feet, in the outer core, a great slow ocean of molten iron and nickel turns. It turns partly because the Earth itself turns. It turns partly because heat rises through it, forming enormous slow currents. A moving fluid of conducting material threaded with existing weak fields regenerates and strengthens those fields over time. This is why we have the planetary blanket of magnetism that shields our atmosphere. A neutron star, at its birth, is briefly something like a fluid. In its first seconds and minutes of existence, the newborn neutron star is not yet fully solid. It is a seething, convecting sphere of incredibly dense matter, hotter than any ordinary star, churning with violence. And it is spinning.
Sometimes it spins at rates approaching the physical limit, hundreds of turns per second. Now, imagine that. In this brief window of fluid churning, a strong dynamo takes hold. The spinning, convecting matter of the young neutron star amplifies its magnetic field by a great factor within the first few seconds of its life. Then, as the star cools and hardens into its crystalline crust, the field is frozen in place. What might have started as a modest field becomes, within a few thousand of heartbeats, a field of monstrous strength. In this picture, whether a neutron star becomes a pulsar or a magnetar is largely a question of how fast it was spinning at the moment of birth. Slow spinners do not build the dynamo. Fast spinners do.
A fast spinning newborn, for a few brief seconds, is a magnetic bomb being wound tight. When it cools, the tightness remains. The second hypothesis is older. It is called the fossil field hypothesis. In this picture, the magnetic field of a magnetar is not created during the collapse. It is inherited. The original massive star, while still alive and burning, already carried a magnetic field through its vast body. Not enormous by magnetar standards, but present, threaded through its wide gaseous interior. When the core of the star collapses, the magnetic field lines are pulled inward with the matter. Imagine a bundle of long, thin threads, initially spread over a cubic volume the size of the Earth. Now crush that volume to the size of a city.
The threads are not destroyed. They are compressed. The density of lines passing through each square centimeter has been multiplied many times over. The strength of a magnetic field depends on how many lines pass through a given area. Crush the lines into a smaller region, and you multiply the field's strength by the same factor by which you shrunk the volume. A collapse from the scale of the Earth to the scale of a city is a volume reduction of about 1 trillion. If even a small seed field existed in the original core, the compression alone could produce a magnetar strength field at the end. In this picture, magnetars are those neutron stars that happen to have been born from stars with stronger than average magnetic seeds.
The field was not made at the collapse. It was amplified once by the collapse itself. A fossil of the original star's own field, preserved in unimaginable concentration. Both ideas have evidence in their favor, and both have difficulties. The dynamo model naturally explains why magnetars seem to be preferentially the children of rapidly spinning cores. The fossil model explains why certain types of massive stars, those with magnetic anomalies in their spectra, seem to be overrepresented among supernova progenitors that leave magnetars behind. It may be that both are partly true, that the final field strength is a mixture of what was there before and what was amplified during the first frantic minutes. We should not be surprised that the answer is unfinished.
We are asking the universe to explain, at the smallest and most extreme scales, how it makes its least likely children. The physics involved touches fluid dynamics, nuclear matter under pressure, relativistic collapse, and the full machinery of electromagnetism in regimes no terrestrial laboratory can reach. We are peeking through keyholes at a forge that neither welcomes nor hides itself, but simply goes about its work. Somewhere, in a part of the galaxy we cannot see, a massive star is now in the last moments of its life. It is about to collapse.
Whether its core will leave behind an ordinary neutron star, a clock pulsar, or one of the rare magnetars is being decided, even as we speak, by the secret interaction of its spin, its field, its convection, its dying pulses of fusion. The decision is being made in a place we can never reach, and the answer will be written into the galaxy for millions of years. There is one more intriguing possibility worth mentioning. Some researchers have proposed that the magnetic fields of magnetars might be amplified further by mergers. When two neutron stars collide, which happens occasionally in the universe, the resulting violent merger could, in principle, produce a short-lived but incredibly magnetic object before the whole structure collapses into a black hole.
These hypothetical magnetar remnants of neutron star mergers would have, briefly, fields even stronger than those of ordinary magnetars, and might be responsible for some of the short gamma-ray bursts observed at cosmological distances. This idea remains under investigation. Observations of the gravitational wave event known as GW170817, a neutron star merger detected in August of 2017, provided important clues about what happens when two such objects collide. The merger produced an electromagnetic afterglow consistent with the ejection of heavy elements, and hints of magnetic activity consistent with a brief magnetar phase. If this interpretation is correct, then some magnetars are not born from supernovae at all, but from the collision of already dense objects, living for only a fraction of a second before collapsing further. The picture that emerges is one of magnetars as a surprisingly diverse family. Some are born from the collapse of massive stars in the ordinary way. Some, perhaps, are born from the collision of neutron stars. Some have fields generated by rapid dynamos in their first seconds of life. Some have fields inherited from their ancestors through compression. All of them carry in their small, dense bodies the most extreme magnetic conditions the universe is known to produce. Different birth stories. One family of monsters. The question of exactly how common each origin is remains open. As more neutron star mergers are detected through gravitational waves, as more young supernova remnants are studied in detail, as more magnetars are discovered and characterized, we will refine the picture. Each new object teaches us something. Each new flare adds a line to the story. The book is being written in real time as the galaxy continues to spin and the observers continue to watch. We are, in a sense, still at the beginning of our understanding. Magnetars as a class of object were only confirmed in the late 20th century. The field is young. Every year brings new discoveries.
It is entirely possible that the magnetars known today are only a small, biased sample of the true population, and that many more exist in states we have not yet learned to recognize. Some might be so quiet that we have mistaken them for ordinary neutron stars. Others might be so rare in their bursts that we have simply missed them. The universe, in other words, is still full of magnetars we do not yet know. They turn in the dark, somewhere, carrying their storms, waiting for the moment of a starquake to announce themselves. Some of those announcements will happen this year. Some will happen in 1,000 years. The sky is always whispering. We are always, slowly, learning to hear more of what it says.
We have asked this implicitly, but let us now ask it plainly. What is the most dangerous object known to science? Not the most energetic. The most energetic phenomena we know are the gamma-ray bursts from distant dying stars, vast cosmic explosions that can, for a brief moment, outshine entire galaxies. They are more energetic, per event, than a magnetar's giant flare. But they are, in most cases, farther. Their cones of death are narrow. They burst, they fade, they do not remain. Not the most destructive per cubic meter. Black holes are the champions of that. A black hole is simply a place where gravity has become so strong that nothing can escape. But black holes, outside their event horizons, are quiet. They do not flare.
They do not sterilize planets at a distance unless they are actively feeding on gas. A slumbering black hole of a few solar masses, 100 light years from your home, would be less dangerous to you than a large rock at the same distance. Not the hottest either. The interior of a young neutron star can reach temperatures of trillions of degrees, but these temperatures are confined, sealed by the crust, radiating outward only slowly. The magnetar is a different kind of danger. It is dangerous precisely because it pairs two qualities that no other object pairs so completely. It is small, and it is active. It is close enough to a regular star in size that it can exist in normal galactic neighborhoods.
And it is capable of releasing in seconds enough energy to sterilize nearby worlds. If a magnetar were placed 10 light years from Earth, we would be in serious trouble before we had even finished asking why. 10 light years.
That is the approximate distance of some of our nearer stellar neighbors. Lalande 21185 is about 8. Procyon is about 11. These are ordinary stars, part of our cosmic neighborhood. Imagine swapping one of them, for a moment, with a magnetar. At 10 light years, the magnetar's steady wind of radiation would already be high enough to degrade Earth's ozone layer significantly over time. This alone would leave the surface exposed to ultraviolet light from our own sun that modern life is not adapted to receive.
Crops would begin to fail. The plankton in the oceans, the foundation of the food chain, would be stressed. Over decades, the biosphere would thin. That is only the steady state. A single giant flare from a magnetar 10 light-years away would be, by any sober estimate, a sterilization event. The high-energy radiation reaching Earth would be enough to ionize the upper atmosphere, to rain down high-energy particles, to damage DNA on any surface exposed to the sky. The ozone layer would not simply degrade, it would be torn apart. The land surface, the lakes, the upper ocean, every place where sunlight normally falls, would be bathed in a dose of radiation sufficient to destroy complex life. The deep ocean might survive. The thermal vents on the mid-ocean ridges might continue to host their heat-loving bacteria. Life, in its most stubborn minimal forms, might hide in the dark and wait. But the trees, the animals, the birds, the fish, the human beings, the cities, and the poems, and the quiet Tuesday afternoons, all of that would be gone. At 1 light year, the effect would be worse. At a few tenths of a light year, the effect would be immediate. Biology would not simply be ended. Chemistry itself, on the exposed side of the planet, would be disturbed in new and severe ways. The surface of the Earth would, for a few hours, be as different from itself as a candle flame is from a cold stone.
This is why, when we talk about magnetars, we sometimes call them the most dangerous objects in the universe. Not because they are the largest engines of destruction, not because they release the most energy per event, but because they bundle almost every form of high-energy output, electromagnetic, particle, magnetic, thermal, into a single compact package, a package capable of firing without warning, from the shadow of a place where nothing seemed to be happening at all. A magnetar does not hunt. A magnetar does not choose its targets. It simply exists, turning, cooling, occasionally cracking. If you happen to be in the wrong direction when it cracks, you do not get a second chance to move. There is a kind of ancient fear that such objects awaken.
The fear of a power indifferent to us. Not a tyrant that hates us. Not a god that judges us. Not a predator that has learned our scent. Just a force, vast and cold and fair, that does not know we are here and would not change its behavior if it did. A being without intention, capable of consuming us by accident. The universe is full of such beings. But the magnetar is one of the most complete examples. It is a storm that has forgotten about us before we were born. And yet, if it chose to stand closer, we would be unable to exist in its presence for more than the width of a single breath. A magnetar's life is not eternal. Unlike an ordinary neutron star, which can sit in quiet darkness for billions of years, a magnetar is expensive to maintain. Its storm costs it energy, and the energy in the field, vast though it is not infinite. Slowly, over long stretches of time, the field decays. This is what separates the magnetar's story from the story of an ordinary neutron star. A pulsar can remain a pulsar for millions or even billions of years. Its spin slows, its beams weaken, but its basic character persists. A magnetar is, in cosmic terms, a brief season. A strange, loud childhood that fades into a long, quiet middle age.
The typical magnetar is believed to retain its extreme field for a time of order 10,000 years. Some are thought to live longer, some less. But the rough answer is that, from the moment of its birth, the storm has, on cosmic scales, only a brief candle's worth of light to give. 10,000 years. A number that feels enormous to a human being. It covers the entire span of human civilization, from the first agricultural villages to whatever we will be in the coming centuries. It covers the rise and fall of every empire, every language, every belief that has ever organized a people. 10,000 years is the longest memory we possess as a species. To a star, it is a breath.
During that breath, the magnetar burns through its field by a variety of mechanisms. The slow relaxation of the twisted magnetic structure inside the crust. The starquakes that crack the rigid shell and release bursts of energy. The steady emission of X-rays, powered not by nuclear fusion, not by gravitational infall, but by the decay of the magnetic field itself. This is unusual among stars. Most stars shine because of the nuclear fusion in their cores. A magnetar shines because of the storm in its skin. Its light is the sound of a field dying slowly. As time passes, the field weakens. The starquakes become rarer. The X-ray glow dims.
The great flares, once every century or so in a young magnetar, slow to perhaps once 1,000 years, then once in every epoch. The star, still rigid, still made of neutron matter, is gradually demoted. Its storm has become a breeze. It is approaching something closer to the lives of its more common cousins. By 10,000 years, most magnetars have lost enough of their field to no longer meet the definition. They are simply, from that point onward, ordinary neutron stars with very long memories. But what happens in the meantime? What does the surrounding universe look like while a magnetar is still young and wild? It leaves traces.
Around some known magnetars, astronomers have detected faint glowing clouds of gas, nebulae shaped by the pressure of the field and the accumulated winds of starquakes past. These are not the tidy planetary nebulae of dying low-mass stars. They are rough, violent, often filamentary structures, aligned along the magnetic axis, their gas heated by the persistent pressure of the star's storm. A galactic traveler who, many thousands of years from now, saw the location of a formerly active magnetar might see a shell of high-energy structure, dimming over time, inside of which sits the now quieter corpse. The storm is over, but the scar remains. The universe keeps its records, even after the hand that wrote them has stilled.
And the magnetar itself, now just a neutron star with a moderate field, continues to cool and spin for the rest of its life. In a few million years, it will be too cold to see in X-rays. In a few billion, it will be a nearly invisible black pebble, still containing its solar mass, still spinning, still bound to follow the gravitational rules of the galaxy. A small, cold witness to a very loud beginning.
If we widen our view further,
If we step back from a single magnetar and look at the history of the galaxy, and then beyond, to the history of the universe itself, we see a slow march of what the universe is becoming. For most of cosmic history up to now, the universe has been full of stars, new ones being born, old ones dying, planets forming, life emerging and fading, galaxies organizing themselves and colliding and drifting apart. This has been, so far, the Star Age. It began about 100 million years after the start of time. It is the age we live in. It will not last. Eventually, over time scales of tens of trillions of years, the reservoirs of gas that feed star birth will dwindle.
The formation of new stars will slow. It will become rare. The last stars to be born in our galaxy will be red dwarfs, small and cool, with lifespans of trillions of years. These will burn slowly, invisibly, for a long time after the bright familiar stars are gone. But eventually, even they will die. After that, the universe enters what has been called the degenerate era, the age of corpses. In this era, the luminous stars have all faded. What remains are the remnants: white dwarfs, neutron stars, black holes. The three kinds of things stars become after they have used their fire. White dwarfs slowly cool, over vast spans of time, becoming dim black dwarfs, objects so cold they emit almost no light at all.
Neutron stars, and the remnants of magnetars that have lost their fields, cool too, becoming dark cold pebbles of ultra-dense matter. Black holes remain, quietly drinking whatever falls close, sometimes merging with one another, but otherwise featureless and silent. In this age, the galaxy will look very different. The familiar spiral arms of dust and young stars will be gone. What remains will be a diffuse halo of stellar corpses, bound gravitationally, orbiting the center, most too dim to see.
They will have come and gone long before this era begins. Their storms were spent within the first few thousand years of their lives, deep in the bright age of the universe. In the degenerate era, every magnetar that ever was will simply be a quiet neutron star in the dark, indistinguishable by eye from billions of its gentler siblings. The fury is gone. The body remains. It is possible, in fact, that on some dry old map of the far future galaxy, a future observer could not tell which dark bodies were once magnetars and which were always ordinary. The memory of the storm fades. The small body cools. The universe, in this way, becomes more democratic over time. The violent and the quiet eventually all look alike.
This is one of the great themes of cosmic time, that every loud thing becomes quiet, that every bright thing fades to black, that every rare and extreme event, given enough time, becomes almost unrecognizable from what was common. Magnetars in this long view are just one of many early dramas in a universe that is slowly moving towards stillness. And still, the movement is so slow. so slow that a human life is nothing at all compared to even the easiest of cosmic clocks. Our entire civilization, all our music and art and sorrow and wondering, fits inside the breath of a single young magnetar. And yet, we have noticed these beings. We have measured them. We have asked them questions.
That, too, is part of the long movement, the slow unfolding. A small and fragile creature on a warm planet, looking out, briefly, at the fire of a dying star and its children. Let us, for one moment, imagine standing on a hypothetical observation platform near such a magnetar, watching its surface from a very safe distance. What would we see? We would see, first of all, a very small object. At a range of, say, 1,000 kilometers, a neutron star the size of a city would appear as a small disk, perhaps twice the size of the full moon in our sky. Its surface, radiating in X-rays and soft gamma rays.
Only with X-ray sensitive instruments could we pick out its details. On such instruments, we might see brighter patches near the magnetic poles, where the field lines converge and the surface is heated more intensely. We might see faint drifts of brightness as the star turned on its axis. We might see, rarely, a sudden bright flash as a small starquake released a burst. And we might see, even more rarely, the onset of a giant flare, beginning with a bright spike of radiation, followed by a long decaying tail that lasted for minutes as the magnetic field lines settled into their new configuration. All of this, radiating steadily into the dark. All of this, from a body smaller than a typical human city.
All of this from an object born from the death of a star long gone, a star whose ashes are now blended into the gas of the galactic arm. We would be watching, from that imaginary platform, one of the strangest citizens of our cosmos. Not a star in the ordinary sense, because it burns no fuel. Not a planet, because it has no atmosphere. Not a black hole, because it has a surface. A hybrid. A rare mode of existence. A way of being that, as far as we know, the universe has only deployed a few dozen times in our neighborhood, and that, in each case, lasts only briefly before fading into the background.
Some thinkers have wondered whether magnetars might be useful, someday, to civilizations advanced enough to approach them safely. A magnetar's energy reservoir, if it could be tapped, would power a civilization for longer than the current age of the universe. A magnetar's precise spin could serve as a cosmic clock. A magnetar's field could, in principle, be used as a vast particle accelerator, channeling charged particles to energies no laboratory could match. These are, of course, speculations. No known civilization has ever approached a magnetar, and the engineering challenges of doing so are almost incomprehensible. Any technology that could withstand the field would itself have to be built from principles we do not yet understand. The magnetar, for now, is simply a subject of observation, not exploitation. We watch.
We measure, we try to understand. The idea of using such an object is closer to mythology than to engineering. But the universe is long. If any civilization ever does last long enough and learn enough to touch such a thing, it will be a very different kind of civilization from any we have yet imagined.
Before we come to the quiet ending of our story, let us take a moment to catalog, briefly, some of the other oddities of the Magnetar, because even after all we have said, we have only brushed against the weirdness of these bodies. In a magnetic field of the strength found around a Magnetar, light itself is forced to behave in unusual ways. There is a phenomenon predicted by quantum theory called vacuum birefringence. In ordinary empty space, light of different polarizations travels at the same speed. Polarization, for our purposes, is simply the orientation in which the electromagnetic wave is shaking. Around a magnetar, the vacuum is no longer empty in the usual sense.
The magnetic field polarizes the quantum sea of virtual particles in such a way that light of different polarizations travels at slightly different speeds through it. This means that a beam of light passing near a magnetar is split. Its horizontal and vertical components separate. What we see at the telescope is a difference in the way they arrive. We have, in recent years, measured this effect.
Two flashlights crossing in a dark room do not scatter. Their photons are oblivious to each other. In the extreme field of a magnetar, that obliviousness fails. Photons can, in effect, see one another bouncing and scattering in small amounts, because the field itself makes the vacuum behave like a weakly reflecting medium. It is as if the magnetar, by sheer force, has turned the emptiness around it into a faint fog. Another strangeness. The magnetar's rotation, as we have seen, is modest for a neutron star, often only one turn every few seconds. This is slow compared to a young pulsar, which might turn many dozens of times per second. The reason is that the magnetar's intense field couples strongly to its surroundings, and it breaks itself quickly.
In its early years, the magnetar loses rotational energy at a staggering rate, not into radiation the way a pulsar does, but into the slow rearrangement of the field. It is as if the magnetar sits down shortly after birth and refuses to dance as eagerly as other neutron stars. Its storm is heavy. It slows itself with the weight of its own breath. Another strangeness. A magnetar's radiation is not smooth. It blinks, it flickers, it grumbles. Within a single second, the measured output can change by factors of many. Within a year, the star might quiet to a low hum, then erupt in 100 small pops, then quiet again. These patterns have no known rhythm.
They are the moods of a body, with storms inside of it. Moods that we, standing very far away, can only record, not predict. Another strangeness. It has been proposed, though not proven, that some magnetars may be related to the mysterious fast radio bursts observed coming from distant galaxies. A fast radio burst is a brief, immensely powerful pulse of radio waves, lasting only milliseconds,
which can be seen across the width of the observable universe. For years, their cause was unknown. In 2020, a fast radio burst was detected coming from a known magnetar inside our own galaxy. It was thousands of times weaker.
It now seems likely that at least some fast radio bursts are the bright voices of magnetars, shouting briefly as their fields rearrange. We have, in other words, heard the loudest known single pulses in the universe, and we have traced the source, at least sometimes, to these rare storm-ridden corpses. Another strangeness. A magnetar's gravity, already severe, can channel matter in peculiar ways. The polar caps glow.
The rest of the star sits dark, while two small bright dots at the magnetic poles burn with pulsed intensity as the star turns. The magnetar, in these cases, is a lighthouse with two flames, both of them made of the infalling gas of its partner. Another strangeness. The very existence of magnetars in their extreme state tells us something about the physics of matter that no laboratory can tell us. They are natural experiments. They give us a testing ground for the behavior of nuclear matter at the highest field strengths. Observations of magnetars have, over the past several decades, refined our models of how atoms and nuclei behave in conditions otherwise found only in the theorist's notebook. The magnetar is not simply a spectacle. It is a classroom.
It teaches us about the limits of the universe by being one of those limits itself. We could list more strangenesses. We could dwell on each one, stretching our minds. But the point by now is almost clear. A magnetar is not a star. A magnetar is a bundle of extremes wearing the shape of a star. A place where many separate improbabilities come together because the collapse that made it insisted on collecting them all in a single small ball. There is, in nature, a certain fondness for concentration. A water droplet is millions of molecules pulled into one shining bead. A crystal is trillions of atoms lined up in one orderly habit. A star is more atoms than any mind can hold, gathered under their own weight into one great round fire. A magnetar is the universe's concentration of exotic physics into a body no wider than a small city. An entire physics textbook, compressed into a spinning bead in the dark. One more oddity worth mentioning, before we leave this long catalog behind. The magnetar's intense field means that, in principle, its surface gravity is modified in subtle ways. The pull on a test particle near the surface is not just gravitational. It is also magnetic. If the particle carries any charge, and even for neutral particles, there are small general relativistic modifications due to the energy density of the field itself.
Einstein taught us that energy is a source of gravity, as much as mass is, and the energy stored in a magnetar's field, as we have seen, is staggering. Part of that energy contributes to the gravitational pull of the object. In other words, a magnetar weighs slightly more than an otherwise identical neutron star, because the field itself has mass, in the strict sense that Einstein's equations use the word mass. This effect is small, only a fraction of a percent by some estimates, but it is real. A magnetar is, in a strict sense, a little heavier than a comparable pulsar, for no other reason than that the field it carries is itself gravitating. Light gravitates. Fields gravitate.
In a magnetar, this abstract principle becomes a measurable contribution. And one more. The extreme fields around a magnetar mean that even ordinary light, traveling near the surface, can, in very particular conditions, convert into pairs of particles. A photon, if it has enough energy and encounters a strong enough field, can spontaneously split into an electron and its antiparticle, a positron, each of which carries away part of the photon's energy. This process, called pair production in strong magnetic fields, is essentially impossible in ordinary space. In a magnetar's magnetosphere, it happens routinely. The field is so strong that it rewrites the rules for what photons are allowed to do. This means that magnetars are, in their vicinity, factories for matter.
They pluck particles out of the vacuum, using the energy of photons and the catalytic presence of the field. The particles they create are almost immediately reabsorbed, or they stream outward along the field lines and eventually decay. But the fact that this happens at all is a reminder that around a magnetar, the distinction between light and matter is blurred. Light can become matter. Matter can become light. The boundary is not erased, but it is thinned, made permeable in a way that no other place in the universe demonstrates. If there is a single word for what a magnetar teaches us, it is perhaps the word extremity. Every property of this object is pushed to the limit. Every feature is an exaggeration.
Gravity, density, field strength, rotational energy, surface temperature, all are at or near the maximum that the laws of physics allow for an object of its kind. The magnetar does not bend the laws. It simply pushes them as far as they can go. For those of us who study these things from a distance, the magnetar is a kind of natural test laboratory. It allows us to ask, what happens when we turn every dial all the way up? And the universe patiently shows us the answer. The answer is a small rigid body, spinning slowly in the dark, radiating softly in X-rays, occasionally cracking its crust, occasionally flinging a flash of gamma rays across the galaxy, occasionally bending the vacuum around itself, occasionally converting photons into particles, and always, always, carrying the most extreme magnetic field known to science. That is what happens when every dial is turned all the way up. That is what the universe at its most concentrated occasionally deigns to build.
We return at last to the beginning of our story. The quiet outskirts of a galaxy, the dying star, the collapsing core, the silent bloom of the supernova, long since faded. The small rigid object left behind, spinning, cooling, carrying its storm of fields. Time passes. A century. 10 centuries. 100 centuries. The star, once a magnetar,
is no longer a magnetar. Its field has weakened. Its starquakes have mostly ceased. It has settled into the long, ordinary life of a neutron star. The children of its bursts, the small clouds of charged particles it once flung into the surrounding space, have mixed themselves into the wider interstellar medium, becoming indistinguishable from the rest of the atoms in that arm of the galaxy.
If any beings in that arm of the galaxy once named this object, their names are gone. Any civilization that might have mapped the sky in that time has long since turned to dust. Their worlds reshaped, their cities vanished, their stories dispersed by the stellar winds of a dozen closer stars. If any observer ever noted the flash of the starquake that 8,000 years ago lit up the neighborhood, that observer is gone. The neutron star continues. It turns once every few seconds. It cools by fractions of a degree per century. Its surface temperature drops, slowly, from the 1,000,000 degrees of its youth towards something closer to the temperature of ordinary things. In 1,000,000 years, it has settled into a faint, steady glow.
In 1,000,000,000 years, it is darker still, barely visible in X-rays. In 100 billion years, it is almost invisible, but it remains. The object itself is as permanent as anything in the universe short of a black hole. The neutron matter holds together. The mass remains. A ball the size of a city, heavier than a sun, dark and cold, continues to orbit whatever it orbited, long after the context of its birth has been erased. Move the clock forward again. The universe ages. The star-forming regions thin out. The bright era ends. Most of the stars around our former magnetar are now white dwarfs, or cooling black dwarfs, or dark neutron stars like itself.
The galaxy at great distance looks like a ghost of its former self, an enormous halo of dark bodies orbiting a central black hole, with faint occasional flickers as old remnants collide or rearrange themselves. The old magnetar is one of these dark bodies, one of many, indistinguishable from the rest. Move the clock further. Now we are in the era that cosmologists simply call the black hole era. The stars, even the small ones, are long gone. The black dwarfs, the cold remnants of once bright stars, have themselves dimmed to near absolute zero. Matter, across vast regions of space, has become too dim to see.
The only large-scale sources of activity are the great central black holes of the galaxies, slowly evaporating over unimaginable stretches of time through a faint emission of radiation named for the physicist who first predicted it, Hawking radiation. In this era, which lasts for a length of time so long that the current age of the universe is, by comparison, the briefest of footnotes, our neutron star and the cold remnant it has become persists. It is by now perhaps 1/10 of a degree above absolute zero. Its matter, still neutron matter in its interior, still mostly its old structure, endures. It has not forgotten the storm it once carried, but it has long stopped feeling the storm.
It is, on cosmic scales, an old blind stone placed long ago in a long cold field by a long dead fire. Eventually, even the black holes finish their slow evaporation. The universe, if our best current theories are right, enters a dark era. A stretch of time so long that all of previous cosmic history is less than the smallest fraction of it. The temperature of space,
approaches absolute zero. The density of matter becomes absurdly low. Only a few last remnants, the old cold corpses of stars, may still exist, drifting alone, separated by distances so large that no event passing in one can ever reach another.
Our former magnetar, if any part of it still exists at this stage, is a dark pebble of neutron matter, perhaps cracked, perhaps reshaped by internal slow processes we do not yet fully understand, perhaps nearly invisible even to the most patient observer. It remembers nothing. It has no mind to remember with. But in its structure, if one could read it, the memory of the old supernova is still there. The memory of the enormous field. The memory of the 30 bursts that, in its youth, shook our upper atmosphere. All of that is written, still, in the arrangement of its neutron layers. It is only that there is no one left to read. And this, perhaps, is the deepest truth we can take from the magnetar.
The most dangerous object in the universe will, given enough time, also become gentle. Its storm will spend itself. Its fires will burn out. Its body will cool. It will sit in the dark, and the universe will pass around it, and the violence it once held will exist only as a fact about the past, not a force in the present. Every monster, given time, becomes a stone. Every storm, given time, becomes a breath. Every extreme, given time, becomes a quiet average. There is comfort in this, in a strange kind of way. Not because the magnetar's fury was wrong. The universe was not trying to hurt anyone. The universe does not try, does not intend, does not aim.
But the arc of cosmic time carries all things, even the loudest and most extreme things, toward a kind of stillness. If there were a way to watch, from the outside, the entire history of a magnetar, from the first flicker of its storm to the last fraction of heat leaving its crust, you would see a great bright tantrum of a thing slowly turning into something old and indistinguishable from its siblings. In our own small lives, we too carry storms. Not of the magnitude of a magnetar, but our own. Brief, bright, apparently important. And we too will, in our own way, cool. We too will quiet. The things that seemed unthinkably urgent to us will, in the long turning of things, become old things.
Small cold pebbles lying in a field. There is in astronomy a beautiful habit of measuring the unimaginable in the language of time. A light year is not a distance, not really. It is a measure of how long light has been traveling. When we say a magnetar is 5,000 light years away, we are saying that any burst we see tonight began its journey to us around the time the first pyramids were being built. The bricks were being stacked, and the gamma rays were already on their way. The pharaoh went to his tomb, and the radiation kept traveling. The Roman Empire rose and fell. The medieval world changed hands 100 times. The Renaissance bloomed. The Industrial Revolution roared. The 20th century arrived.
And still the radiation was traveling. Only now, at this moment, does it arrive at our detectors, carrying its quiet announcement of an event that happened in the deep past, in a part of the galaxy that by now has long since moved on. The light we see is always old. Everything in the sky is, in some sense, a memory. The sun we warm our faces in is 8 minutes old. The nearest stars are years old.
The Andromeda Galaxy, our nearest large neighbor, is 2.5 million years old when we see it. A magnetar flare recorded this year may have been released during the age of the pharaohs, or during the time of the dinosaurs, or during an epoch when the continents of our planet were differently shaped. The sky is a great archive of old news. We are, always, reading telegrams from long-dead senders. And the most beautiful part of this is that, when we see a magnetar, we are not only looking at the present, we are looking at a version of the object that no longer exists. The magnetar we observe from thousands of light years away may already, in its own local time, have decayed into a quiet neutron star.
The burst we see tonight may have been, in its own frame, the last such burst that object will ever produce. The object itself has moved on. Only our view of it remains frozen in the past, slowly resolving as the light continues to arrive. This is the deep strangeness of an ancient universe. Every observation we make is, by necessity, an observation of history. There is no such thing in astronomy as the present moment on a distant body. There is only the present moment here and the record of the past arriving from there. When we speak of magnetars, we are speaking, always, of ghosts. The lights we catch are the echoes of events that have, by now, passed into silence.
And that, too, is part of the kinship. The magnetar sends us news of its own storms from a time long past. We receive that news in our small, warm rooms. We turn the news into knowledge. The knowledge becomes part of the slow, patient understanding that our species has been building, piece by piece, for a few thousand years. And this understanding, in turn, will fade, in its own time, into the long silence that awaits all loud things. It is not a diminishment. It is a kind of kinship. We share with the magnetar this one thing, that what we hold in ourselves, no matter how strange or intense, is not meant to be held forever.
It is meant to be felt, and to pass, and to become part of the long, quiet average of the cosmos. And so, with the old magnetar now dark and still in its corner of the sky, we have come to the end of our visit. Far above us, somewhere in the immense volume of our galaxy, there are at this very moment perhaps 30 of these objects, rare and loud and indifferent, writing the pages of the present chapter. Perhaps a handful more, hidden in dust, waiting to be found. Each one is carrying, inside its small rigid body, a storm we cannot imagine, and inside that storm, the patient seed of its own long silence. The silence will come. It always does. Until then, they turn, and they burn, and they do their strange and lonely work in a universe that will outlast them all by spans of time beyond every clock we know how to read. Close your eyes now. Listen, if you can, for the deep, slow rhythm of the dark. Somewhere out there, past the last light of our sun, past the quiet neighbor stars, past the wide river of the galactic arm, a small, rigid body turns, once every few seconds, carrying the most dangerous field our universe has ever made. It does not know we are here. It never will. And that is, in its own way, a gift. We have been given a sky that burns, far away, without burning us.
We have been given the freedom to notice, from our safe green world, the extremes of what the universe can become, and to sit with those extremes and to wonder at them, and to let our wonder carry us gently into sleep. The magnetar turns, the galaxy rolls. The long night unfolds around you, patient and kind. Rest now. Rest and let the strange distant storms carry on without you. They have their own work. You have your own quiet. Both will hold. The sky is wide. The dark is soft. The magnetar far away is doing what it was made to do. And you are doing what you were made to do, and the great slow symmetry of the cosmos folds you both into the same long turning.
Good night. Sleep well. Total 17,500 words, 12 chapters.